Section 1.2, Initial Value Problems. So let's start by looking at the definition of what we mean by an nth order initial value problem. An initial value problem has two parts. First, the goal is to solve just an ordinary differential equation. I'm going to go ahead and write one down in normal form because that'll be the most common format that we put ours into. Let's say you start with a differential equation of nth order in normal form, so it's solved for d and y dxn. So that would be some function of x, y prime, all the way up to the n minus first derivative. But in addition to the differential equation, we're going to include an initial condition, or a set of initial conditions on this differential equation. An initial condition would define or constrain the value of the function at a single starting point, x naught, to be y naught. So y at x naught is equal to y naught. Now for an nth order initial value problem, we're going to have n conditions. So in addition to y at x naught being y naught, we're also going to constrain or apply a condition at x naught to the first derivative. So y prime at x naught, we'll call that y1. And we'll do that for y double prime, y triple prime, all the way up until we get to the n minus first derivative at x naught. We're going to say that's y n minus 1. Now in each case, x naught, y1, y2, all the way up to yn minus 1 are numerical values that would be provided in a specific problem. Now as I said, there are n of these here that you'll see included in the problem. It looks like there's only n minus 1 since I only went up to n minus 1 here, but realize that I did start with 0. So by starting with 0, I've now included n of these initial conditions. Now just for reference, let's look at what this would look like if we're talking about a specific first order differential equation. And again, by the way, let me point out, this first part up here is simply an ordinary differential equation, and I'm going to refer to that as the DE or the ODE. And then these down here are the initial conditions. And we think of them as initial conditions because we think of x naught as being the starting point. And so we're applying a condition at that initial point in time. In many cases, that x naught is going to be 0, which would make sense if you're thinking in terms of your independent variables, say in terms of time. Then x naught equals 0 would mean at the start point, at when time equals 0. But in other applications, it may make sense to start from a different initial point. But in every case, we're going to start from the same point in each of our constraints. Now, if we did look at a first order system, that means we're going to have simply dy dx equals some function of x and y, and we'll have a single initial condition called y of x naught equals y naught. Okay, our second order initial value problem would look like this. It would be the second derivative of y with respect to x, and then your function would depend on x, y, and y prime. You'd have a y of x naught equals y naught, and a y prime of x naught equals y1. You have two initial conditions because it's a second order differential equation. So let's consider this particular initial value problem where we have dy dx is equal to y, and then our initial condition is y of 0 is 3. Now you'll recognize this problem from calculus. It says that there's a derivative of a function is equal to itself, and we know that the function y is equal to c to the x is a solution to this differential equation, because if you take the derivative of y ce to the x, you'll end up with ce to the x. So plugging this into your original differential equation up top, you're going to see that the derivative is ce to the x, and then the original function is ce to the x. Check. That satisfies the differential equation. Now, how do we find a solution to the initial value problem? This is actually an infinite family of solutions. It's a one-parameter family of solutions because this would solve the differential equation for every value of c, no matter what c you plug in. Now, there will be only one solution for the initial value problem, that is, this problem as a whole, because of the initial condition. So how do we find the solution to the initial value problem? We plug in our initial condition. Our initial condition is y of 0 is equal to 3, so we're going to plug in 0 here n for x, and 3n for y. So that means c e to the 0 is equal to 3. That is, I'm plugging it into my solution, right? Now, e to the 0 is 1, so c times 1 has to equal 3. We have found the value of c, so if we plug that into our general solution, or our one parameter family up here, plug in the c equals 3 right there, you end up y is equal to 3 e to the x. And that is a singular or specific solution to our differential equation. Not just our differential equation, but our initial value problem. Okay. So let's try the next one. Again, we're going to start with y prime is equal to y. Now I'm going to use y of 1 is equal to 2. So a slightly different initial condition. So we'll have the same solution in terms of the solution to the differential equation. Y is equal to c e to the x. Now the question is, what's the specific or unique solution to our initial value problem? Plugging in 1 for x and 2 for y, we get c e to the first is equal to 2, which would be c is equal to 2 e to the minus 1. And we get that from basically just dividing from here, divide e to the other side. It looks like c equals 2 over e, and 2 over e is just e to the minus 1. So plug that into your solution, which your solution was y equals c to the x. That's the general solution to the differential equation. And now we plug in 2e to the minus 1 in for c, and we can simplify that by rewriting it as y is equal to e to the x minus 1. And that solves our initial value problem. All right, in our next example, we're going to talk a little bit about what we mean when we talk about the interval of definition versus the domain of the function. To begin with, let's just do the same thing we've done on the previous two examples. First, verify that the function y is equal to 1 over x squared plus c is a solution to the ODE, namely this differential equation right here. And then we're going to find the c by using the initial condition here. So first of all, we need to take the derivative. The easiest way to take the derivative here is to think of 1 plus x squared plus c as x squared plus c to the negative 1. So you bring your minus 1 out front and reduce your exponent by 1, so you have a negative quantity x squared plus c raised to the negative 2. And then times the derivative of what's inside, which would be times 2x. Or rewriting that, that would be a negative 2x over x squared plus c quantity squared. Now I'm going to plug this guy right here into the differential equation right there. And then I'm going to plug the original y into here. And as a result, this is what you get. You'll see a negative 2x over x squared plus c, all quantity squared. Then you see plus, and you have 2x times the original function y, which would be y squared, which would be 1 over x squared plus c quantity squared. And the question is, does that equal to 0? And clearly it does when you just multiply in the 2x to the numerator of the second term here. Then you end up seeing, yes, that is, in fact, 0. Now let's find the c that goes along with the initial value problem. Okay, so we're going to use the initial condition y of 0 is equal to negative 1. So plug in 0 for x and negative 1 for y. That gives me 1 over 0 squared plus c is equal to negative 1. That's 1 over c equals negative 1, which means c has to be negative 1. So my final answer to the initial value problem is y is equal to 1 over x squared minus 1. Now, the question is, for what values of x is that the solution? Which, by the way, is a different question than asking which values of x are in the domain of that function, right? We can plug in a certain set of numbers, but the question is which ones serve as a solution to that initial value problem. Okay? So, the largest interval over which the function y is defined and differentiable and contains the initial condition, that is what we're going to call the interval of definition. Now, for our function, this one right here, the domain is going to be the set of all x's except for negative 1 and positive 1, right? Or real numbers, take out negative 1 and positive 1, because if you take the denominator and set it equal to 0 and solve that for x, you get x is equal to plus or minus the square root of 1, or x is plus or minus 1. Those are numbers you can't plug in because that makes the denominator equal to 0. Another way to write this domain is it's all numbers from negative infinity up to 1, union with negative 1 to 1, union with all numbers from 1 to infinity. So that leaves out negative 1 and positive 1. You can see that by just looking at how this thing graphs on a real number line. Now, what's the interval of definition? Well, if you use this answer that I just gave you right here, the largest interval over which y is defined and differentiable and contains the initial condition. So think of this last part as the most important part. It contains the initial conditions. So if it's going to contain the initial conditions, it has to contain the point where x is equal to 0 and y is equal to negative 1. So these are the values of x's that you can plug in. 0 is in this interval right here, so the interval of definition is negative 1 to positive 1. All right, now I'm going to take a break and go over to a browser for a second. We're going to take a look at this tool where we can kind of explore how the interval of definition works with a couple of different initial value problem examples, and we can do it visually through the browser. So I'm going to go over to snipurl.com/DEtool to take a look at that.
Now I've gone to the URL, snipurl.com/DEtool. This is a tool that's available with our textbook. I'm going to go to the interval of definition under Chapter 1 and take a look at some examples. Now the first function I want to start by looking at is the actual function 2xy squared. That is the f of x comma y is 2xy squared. Very similar to the problem that we did in the notes, but not exactly the same. In fact, it's just off by a sign here, since I have moved the 2xy squared to the other side. We had a positive 2xy squared on the same side as the derivative in the example. But I could still make the case of what I wanted to demonstrate with this particular function. What you see on the screen right now is the solution to an initial value problem. You have the differential equation right here. The dy dx is 2xy squared. So this curve that you see on the screen is a function that is a solution to that differential equation. Now if I then impose a specific initial value, namely that y at 1 is 1, that's this point 1 comma 1, this is the unique solution to this differential equation. Now notice if I click on and drag this point around, what I see is a whole family of solutions, all of which satisfy that differential equation, and each one of them is a unique solution to a specific initial value problem. Now when we talk about the interval of definition, remember it's the largest interval, right, that contains the initial conditions. Basically what we're looking at here. So in this case, the solution to the initial value problem, in fact I'm going to come down here to this slider, I'm going to put the slider at 2 and this value out here at 1. This says y of 2 is equal to 1. The interval of definition is only this interval between the dotted lines. It's only the curve in red that is a solution to your initial value problem. On the other hand, if I were to move this point down here to say, let's put it back at 2. Initial condition y of 2 is equal to a negative 1. Then now the solution to the initial value problem is this curve in red, and the interval of definition is from this dotted line, roughly a little more than 1.5, maybe 1.75 roughly, up to positive infinity. That is your interval of definition. All right, now if you switch over to other differential equations, notice how your interval of definition always contains your initial conditions, and it's the largest interval that contains your initial condition over which the function is continuous. I can't go past, say, this dotted line in this example because the function is not continuous across the dotted line. So you see where the interval of definition moves based on where your initial condition is. Okay? By the way, it just so happens that if you recognize this curve, it is in fact what you might think it would be. It looks like the tangent curve, and in fact it is. You can double check the derivative of tangent is, you'll probably recall it as secant squared, but secant squared is also 1 plus tangent squared. If tangent's your y, then 1 plus tangent squared is 1 plus y squared. This is the tangent function. Right? So your interval of definition in this case happens to be negative pi over 2 to positive pi over 2, where the dotted lines are what range of x's over which your solution is defined. So the red curve solves the initial value problem.
All right, now let's look at the second order initial value problem. In our previous examples, we were doing first order initial value problems. So now we're going to look at a second order. As before, we're going to assume we know the answer. X is equal to C1 cosine 4t plus C2 sine of 4t. We're going to say, let's know that that's a solution. Let's find the solution to the initial value problem. What's a little bit different about this now is that in order to use our initial conditions, we're going to have to use the original function, but we'll also have to use the derivative. So the first part's the same. Just plug in the initial condition, which is x of pi over 2 equals negative 2, which means we're going to let t equal pi over 2 and x be equal to negative 2. So plug that in. You end up with, plugging it into here, where there's a t, put pi over 2, and over here where there's an x, put negative 2. So you end up with negative 2 equals c1 cosine of 4 pi over 2 plus c2 sine of 4 pi over 2. 4 pi over 2 is actually just 2 pi in both cases here. So cosine of 2 pi is positive 1 and sine of 2 pi is 0. So you end up with negative 2 c1 times 1 plus c2 times 0. So we're fortunate here that the c2 drops out, and we see that c1 is just negative 2. Now, in order to use the second initial condition, we need to know the derivative of this function right here. So we're going to take the derivative of that. Derivative of cosine is negative sine, so you're going to end up with a negative 4 c1 sine of 4t plus a 4c2 cosine of 4t, plugging in, again, pi over 2 for t, and this time, for the derivative of x, we're going to plug in 1. We have 1 is equal to negative 4c1, 4 pi over 2, plus 4c2 cosine of 4 pi over 2. Those are both 2 pi, and sine of 2 pi is again 0, cosine of 2 pi is 1, so you end up with 1 is equal to negative 4c1 times 0 plus 4c2 times 1. So 1 is equal to 4c2, so c2 is 1/4. Plug that into your original solution, and you have x is equal to negative 2 cosine of 4t plus 1/4 sine of 4t. That is the solution to that second order initial value problem. Now, one question that we will often ask in a mathematics course when we introduce a new type of problem, especially one where we're seeking the solution to a problem, is how do we know a solution even exists? So the question we really haven't even answered yet is, do we know? Does a solution exist? In addition to that, we'll also want to know, if it does exist, is it unique? Right? And we even have mathematical symbols to represent that. Exist, we usually use a backwards E. For unique, we put a backwards E with an exclamation point. Now, just by way of example, consider the following initial value problem. dy dx is equal to x, y to the 1/2, and y of 0 equals 0. I claim this guy right here is a solution to the initial value problem. Now, why is it a solution to the initial value problem? Well, one, if you took its derivative, you would see its derivative is the same thing as x times the square root of that function. Checks out, works just like you'd expect it to. Okay? So this is a solution to this differential equation up here, and it also satisfies the initial conditions, because if I plug in 0 here, I get y is equal to 0. Voila, that works. But the question is, can you see another solution? And if you don't see it right away, always go back to the trivial solution and see if it works. The trivial solution is y is equal to 0. Why is it called a trivial? Because it's the one that's just obvious. Try it. If it works, then there's no work at all in terms of solving it or finding the parameters or anything like that. No work involved. It's trivial. Now, since it's a function, you can take its derivative. The derivative of a constant function is equal to 0. So that over here on the left-hand side would be 0. And then if you plug in 0 for this function here, y, you get 0 is equal to x times the square root of 0, which means 0 equals 0, so it works. And it also satisfies the initial condition. So we have a problem here where there are two completely independent solutions. Now, I'm not using the phrase linearly independent here. I'm just saying two different functions, not identical functions. The only place these two functions agree is at 0. Everywhere else, these two functions are different values. So these are not identically the same function in any way, shape, or form. You've got y is equal to 0 and y is equal to 1/16 x to the 4th. So it's apparently possible to have initial value problems that have multiple solutions. Now, how do we know on all our previous examples that the solutions that we came up with were our only solutions? Well, there are ways for us to confirm that. In fact, I'm going to give you one theorem here, which is a rather weak theorem, and we can make it more stringent, meaning, well, I should say, the conditions here are actually relatively strict. If you were to go on and take a graduate level differential equations course somewhere down the road, you would learn that, in fact, we can make this significantly less strict and still be able to guarantee that the initial value problem has a unique solution. But in this case, let's go ahead and move forward and say, okay, we know that we've got this first order differential equation right here. dy dx equals f of xy, y of x naught equal y naught. And I'm just going to state the theorem just for reference so you can see what these kind of theorems look like for a first order system. Let's start with the rectangle AB cross CD, okay, such that our initial condition is inside this rectangle. So let's draw a picture here. Let's put x naught, y naught on the graph. And by the way, what we mean by AB cross CD, that's the Cartesian product. If you take any two sets and you come up with their Cartesian product, what that means is it's the set of all ordered pairs where the first part of the coordinate A is in the set capital A, and the second one, little b, is in the set capital B. So if you think of this AB right here as it's an interval, it's a closed interval from A to B, and this is the closed interval from C to D, put A and B around x naught and C and D around y naught, then the rectangle R is the Cartesian product of those two closed intervals, meaning it's that rectangle and everything inside of it. So this is a picture of x naught, y naught being inside of the rectangle R. Now, if you can find a rectangle R so that f and the partial derivative of f with respect to y is continuous everywhere on that rectangle, then there exists a unique solution to the initial value problem over some interval around x naught that's inside of AB. That's the condition. You have that the function, it's continuous, and its partial derivative with respect to y. Now, it has to be a partial because f now depends on two variables here, and we're saying the derivative with respect to the y variable here, if that is continuous on some rectangle, closed rectangle that contains x naught, y naught, then there is some unique solution around x naught. That is on some interval around x naught. We know there's a y that is a solution there. Okay? The little width of this interval right here is h. It's got to be somewhere inside there. We know that there is some interval around that where there is a solution, and that solution is unique. Okay? By the way, I refer to that I right there as our interval of definition. Now, the theorem here, let me point out, is necessary, but it is not sufficient. Now, what I mean by that is that the conditions of this theorem don't go both ways. I mean, it's not a biconditional or an equivalent statement. You can have initial value problems. There are initial value problems with unique solutions that don't satisfy these conditions. On the other hand, if it satisfies those conditions, we know it has a unique solution. So all initial value problems that satisfy these conditions in the theorem have unique solutions. So why did the previous example that we did not have a unique solution? The example x squared to y, or x y to the 1/2. Well, think of the partial with respect to f. The partial of f with respect to y. The partial of f with respect to y would be x over 2 y to the 1/2. Just treating x as a constant, bring the 1/2 out front, drop that power by 1, you end up with this function right here. But what's the problem with that? Well, think about where your initial condition is. Your initial condition is x equals 0, y equals 0. Okay? So for the function x over 2 square roots of y, we know that it's only defined when y is strictly positive. It can't be defined for y equals 0. Right? And if the initial condition is y equals 0, then y has to be 0 for your initial condition. So that partial with respect to y of f is not continuous on any rectangle that contains 0, 0, which means we're not guaranteed a unique solution in this case. Okay? So I threw in this theorem here at the end. We're not going to prove it. You'll have very little to do with the theorem itself in the homework, but I wanted to make sure that you saw that this kind of question, the mathematical question of whether or not a solution exists and is it unique, is relevant, and in many cases can be a very important question to be able to answer. Obviously, if we can't guarantee uniqueness of solutions, then we have a whole world of problems that open up to us that we don't know if we found the only solution. But in most cases, the functions that we look at in this class, we're going to be able to verify formally, beyond the shadow of a doubt, mathematically proven that it's going to have a unique solution. So that's the end of section 1.2.